wondered what it's like inside the Earth? Tremendous heat energy is stored beneath our feet, energy that was created in part by nuclear radiation. Nuclear radiation is the result of the natural disintegration of the basic fabric of matter, the nucleus of an atom. It's a process that occurs most often in elements heavier than lead, such as uranium, which have relatively large nuclei. These nuclei are unstable. That means that there's more particles than are needed. Excess particles are shed, and these become particle radiation, or radioactivity. Once the particles escape from the atom, they usually run into something. When they stop, their kinetic energy is turned into heat. This is the process taking place inside the Earth. Radioactive minerals generate heat, which is built up over billions of years. This heat energy escapes, usually carrying a lot of steam, ash, and lava with it. Nuclear reactors work in a similar way. They just speed the process up by concentrating the uranium into dense pellets. With many unstable atoms close together, the particles from one nucleus can split other nuclei apart, radiate more particles, which in turn split more nuclei, and so on. This is a sustained nuclear reaction. The activity from all this particle motion generates heat, which can boil water, make steam, and run a turbine in a nuclear generating station. Nuclear radiation comes in three forms: alpha, beta, and gamma. Alpha particles are the heaviest and the slowest, if you call 15 million meters per second slow. They're actually the same as the nucleus of a helium atom. They have a positive charge and can be detected by a Geiger counter. The energy of these particles is low enough that they can be stopped by a few layers of paper. Beta particles are the size of electrons, much smaller than alpha particles. They have a negative charge and have about 100 times the penetrating ability of alpha particles. We've already seen that gamma rays are part of the electromagnetic spectrum and can be described as waves that move at the speed of light. Although they're electromagnetic radiation, they come from the nucleus, not the outer electron cloud like other electromagnetic radiation. They're incredibly high frequencies, and their high energy enable them to penetrate steel. When a material like uranium is naturally radioactive, its atoms are disintegrating. That doesn't mean they vanish, they simply turn into another form. One form of matter, the parent, turns into something else, a daughter material. Uranium, for example, is a parent that turns into thorium, a daughter compound. This process is called decay. Decay happens at a specific rate depending on the material. It's important to know how long it will take for the parent to completely decay into the daughter, because the daughter will be less radioactive. Radioactivity never completely stops. It just gets so low it's almost unmeasurable. So the unit of half-life is used. This is the period of time it takes for half of the original material to decay into the daughter substance. Half-lives can be as long as thousands of years, or as short as a few minutes. Materials with extremely short half-lives are not easily found in nature because they decay so quickly, but they can be made artificially and are extremely useful. Almost anything can be made radioactive when exposed to particle radiation. The process is called artificial irradiation. The product is called a radioisotope. A radioisotope is any material that becomes radioactive when irradiated. Once radioactive, it gives off its own radiation. The amount it gives off depends on how long it was exposed. This has become a new tool in diagnostics, both in medicine and in industry. Steve Fay is a technician who uses radioisotopes to produce pictures of activity within the body.
Okay, what I've done is I've started a bone scan on one of my patients that I injected about 2 hours ago. The patient was injected with technetium 99M HDP. It has a 6-hour half-life with a real low energy level. We collect 400,000 gamma disintegrations because the radiation we're detecting is a gamma ray. This is the total body scan of the patient that we saw earlier. It's developed on an X-ray film, and it just gives us a skeletal image of the patient. And you can tell by looking at this that the patient has bilateral arthritis in the shoulders and the elbows, and you can see this because of the increase in the radiation, the radioactivity in the shoulders and the elbow area, and maybe in the knees also. The radiation that is received in nuclear medicine is very safe. It's much safer than X-ray, in that X-rays cause secondary radiation, where the gamma rays received in nuclear medicine cause very little secondary radiation. It has a short half-life, most of it. Its biological half-life, as far as the patient is concerned, is even shorter than its own half-life, its physical half-life, which makes it safer. It washes out of the body very easy and very rapidly through the urinary system. I would rather have a nuclear medicine scan than a CT scan because the radiation dose is less.
Radioisotopes have introduced an entirely new area of medicine called nuclear medicine. Low-dose, short half-life labels enable doctors to watch drugs act in the body. By labeling the drugs with radioisotopes, instruments can sense the presence of the drug by the glow of the radioactive label. One of the most sophisticated is the PET scanner, positron emission tomography. The PET scanner picks up radiation coming from inside the body given off by the radioisotope labels. A computer constructs the information into a cross-section of the brain. Instead of just seeing general structures of the body, the PET scan shows actual chemical reactions taking place during the process of thinking. This is how activities within the atom provide information about activities within the body. Because extremely small quantities of radioisotope materials can be easily detected by instruments, they can be used as tracers inside technology. For example, in our last unit, we looked at a transducer called a turbine flow meter. Suppose you wanted to check the flow rate at a specific point in a high-pressure steam pipe that a flow meter could not handle. By injecting a small amount of a radioisotope into the steam, a detector outside the pipe could monitor its passage, measuring the flow rate without interfering with the fluid. If the isotope has a half-life of a few hours, the steam would be harmless shortly after the measurement is made. Non-destructive testing enables technicians to look inside machines without taking them apart. Suppose an engine part is irradiated before the engine is put together. Looking for radioactivity in the oil after running the engine will tell you how much of that part material has worn off without taking the engine apart. Gamma ray detectors are often used to spot flaws in welds. Like all radiation, exposure to large doses of nuclear radiation can be hazardous to your health. If you're overexposed, tissues in your body can be damaged. That's why the number of PET scans you can have in your life is limited. Carefully controlled exposures can get rid of unwanted tissues, such as cancer cells. Properly controlled and properly understood, nuclear radiation can provide penetrating energy and a new window that enables technicians to see inside technology and inside the body.